we are going to discuss resistive or resisting or opposing force on the object moving with less speed in the viscous medium. So I'm writing, consider an object moving with less speed. So we are taking magnitude of velocity, less speed in a viscous medium. Then it is found that, okay, it is found that resisting force is directly proportional to object velocity, provided the velocity is small, okay. So we have this condition, we can see, for object moving with less speed, okay, in a viscous medium, resisting force is directly proportional to the velocity. So we have this, okay. So this holds when velocity is small or when the speed is small, okay, is small. So we have this. Now let R be the resisting force and vector V be the velocity of the object. Therefore, R proportional to velocity of object, and we have negative sign in this relation, and negative sign indicates that R and V, that is resisting force and velocity, are opposite. So from this relation, okay, after removing proportionality, we have this, okay, minus B times velocity of object, and B is constant of proportionality, okay, which depends on the properties of the medium, that is viscous medium, shape and dimension of the object. So we need to note this, okay. So what we find for object moving with small velocity, okay, resisting force is directly proportional to the object velocity. So we have this, okay. So this is to be noted. Now consider vertical motion, okay, of an object. So I'm drawing over here. So we have object moving down, okay. So the motion is down, and let the velocity of the object be vector V, okay. So we have this. Now the weight of the object acts vertically down, and since the motion is downward, okay, resisting force acts upward. Okay, so I'm writing in magnitude, okay, resisting force or opposing force. Now let us take this sign convention, okay. Let us take vertical direction as positive and upward direction as negative. So we have this. So we have plus y, okay, in downward direction, and we have negative y in upward direction. This is simply a sign convention, okay. Now what we find, okay, in this case, we find total force acting on this object, okay, total force acting on this object, that is summation F equals mass time acceleration. Since the object is in motion, so it has acceleration, okay, and is moving down, so the mass is m. Now we can see in this object moving downward or is accelerating downward, we have two, okay, force, and we neglect, okay, we neglect buoyant force, okay. So we see there are two forces, okay. We have neglected the buoyant force. One force is the weight acting in vertically downward direction, and another is the resisting force, okay, acting in upward direction due to the medium, okay, due to the viscous medium surrounding the object. So what we do is that from this equation, we write mg minus r equals m, and we can write acceleration a equals rate of change of velocity, okay. So we have this. So using this, we write in this way dv by dt. So dv by dt, okay, equals mg by m minus r by m. So this cancels out. Therefore, dv by dt, okay, rate of change of velocity equals g minus r by m. So we have this. Now we know from this equation, okay, magnitude of resisting force R equals B times V. So we have this, okay, because negative sign indicate that resisting force and velocity, they are opposite to each other. So we are going to put, so let's call it equation 1, okay. This is equation 1, and let's call it equation 2. So I'm writing in this way, okay. So what we do now, from 1 and 2, okay, dv by dt equals g minus and r, magnitude of resisting force, this is b times v, okay, divided by m. So we have this. So let's call it equation 3. So we have this. So writing over here, we have this relation, okay. I'm erasing this, okay. So we have this, okay, dv by dt equals g minus b times v divided by m. This is equation number 3, okay. So I'm rewriting equation number 3. Now, as the object moves downward, we see we have motion in downward direction, okay. And if we get a stage at which the weight mg balances the resisting force, so I'm writing if mg is balanced by r, okay, that is resisting force, then object moves, okay, with zero acceleration. That is what we get. This, okay? This force is 0. Okay, so we can write in this way also. A is 0, okay? Acceleration is 0. So if mg balance r, then the total force acting on the object is 0. It means that the acceleration is 0. So what we find? Therefore, if the acceleration is 0, okay? If a is 0, so a means rate of change of velocity is 0. So if we have this, then from 3, okay, we get this. 0 equals g minus b by m times v. Now, okay, we have this. So if the object moves with 0 acceleration, okay, then at this point or this stage, the object moves with the speed called terminal speed, okay? So I'm writing over here. At this point or stage, the object moves with speed called terminal speed, okay? So let us denote terminal speed by the symbol Vt. So object moves with speed v equals Vt when acceleration is 0. So when acceleration is 0, then we have to replace v by Vt. So I'm simply writing in this way, okay, where v is replaced by terminal speed, that is Vt. So therefore, we can write v times Vt by m equals g. Therefore, terminal speed Vt equals gm by b. Clear? So this is the required expression for terminal speed, okay, for an object moving in vertical downward direction, okay.